Okay, we have talked about on-state power loss, which is conduction loss, so-called conduction loss. So conduction loss represented by when we switch on the circuit, or switch on the device, how much actually the resistance across the switch during switch on, and on transistor, how much actually the power voltage drop across the transistor during switch on. Now we shall see in terms of how much actually, instead of only conduction loss, so how much actually the switching loss to include inside your calculation to be the sum of PD total, which is the sum of switching loss and together with the previous conduction loss. So we shall see that when we switch the circuit, and this is the transistor V drop, voltage drop, during switch on. When we during the switching itself, there is a response whereby when the increment of current take place and the dropping of V across your drain to source is dropping, the response is some sort like a delay here. So this area will be your losses during switching, which is P loss is equal to V times I times the area below this part divided by 2, and area or the length here divided by 2. Okay, this is the amount of your switching loss, whereby your conduction loss here is happen during the conduction of P equal to V also V drop, and V drop times the amount of current that passing through your circuit, average or RMS. So this is the drop that you have to consider for the switching and your conduction loss. So let's take a look again on the slide, which is, see here we have sorry, mana pergi gelap cursor tu. Okay, set over here, conduction loss is the current and due to the RDS on of the transistor. This is referring to MOSFET. Conduction loss is the current, the load current here squared times RDS on. For transistor, your conduction loss will be V times voltage drop. Current times voltage drop across your transistor. Okay, as we can see, the real device will dissipate power when they are used in various applications, and when they dissipate too much power, it will build heat inside the junction. The device can fail. So it does not only destroy the device itself, but the other system as well, and so it will be effect to the system. And much more that we can see, the power device is the main part inside our converter. So once your component is damaged, so means the whole system is breakdown. Okay, you can see over here, this is the range of frequency for switching from 10 kHz up to megahertz range. Usually megahertz is applied on the communication side, but for power switching, we only apply up to kilohertz, up to 100 of kilohertz. Why we take 10 kilohertz and above, usually 20 kilohertz and above? Why is that? It's due to the audible noise, the frequency that can be catched by our ears and our audio system. So we can hear the frequency switching, the buzzing, the humming of below below 20 kilohertz. Above 20 kilohertz, it does not what's so called pollute or does not interrupt with our audio lah. And so that's why switching is usually set at 20 kilohertz and above, but cannot be set too much higher, because once you increase the switching, so the switching losses will be dominant and the efficiency of the system will reduce from 100% down to several of worst case 50%. And usually we shall maintain our converter to be less than 10% of losses. So the PD total here will be the sum of conduction loss plus switching loss. Okay, this is how the theoretical response will be. You can see that we can follow the switching test circuit inside datasheet. Some datasheet they provide with this kind of test circuit switching arrangement. So consider a pure resistive load. So we connect our VDD here, DC source, to the load, and the load will be connected into our switching device, on off switch. So ground, source, load, switch, ground. Okay, assume this is a MOSFET, so it will be derived by a gating signal, a voltage gating signal. So for your simulation, you can set any simple gating signal, but for actual driving, you shall need to consider how much actually this MOSFET need as our gating voltage. Minimum maybe around 10 volt, maximum maybe around 20 volt, and how much actually the current that needs to be driven or supplied to the gate. So determined by this RS, the series resistance of our gating signal circuit. Usually they put 1K, and here we put 20 volt, like that. Okay, when we perform the simulation, we shall see that there is a response between when we turn on, and VGS will be at maximum range of VDD here. So this is GS here, maximum of VDD here. So this is our V from drain to source. And so when we switch on, means that there will be a depleting voltage from our drain to source. Means that it will be connected, so the voltage will drop, and at the same time the current will rise, and will rise to maximum. V will drop to minimum. It will not drop to 0 because we have here conduction or voltage drop, and there is a what's called a threshold voltage. It still has voltage values even though you switch on, because this is not ideal. This is not an ideal circuit, an ideal switch. There is voltage drop across the switch or across the diode, and when you switch on, so it will contribute to the conduction loss. And during transition, it does not turn off abruptly or suddenly, but it has a delay. So this delay will contribute into our switching loss. So this is so-called time to turn on and time to turn off. So when we plot in terms of switching signal versus the switching signal on or off versus the response between VDD and I load and the power that generated of the losses, generated power of losses during switching and during conduction. So this is the pattern, the waveform of the instantaneous switch power loss during switching and during conduction. So the sum of this switching and conduction times the frequency that we apply, so we shall get our losses, total losses of the system or of the switch. Okay, so you can see here when the switch is start, so we still have a time delay. This TD here is time delay. You can see, even though we apply the switch on at the gate, we have a delay. So time delay will determine in terms delay time before the I load to rise, and also V from drain to source only to reduce when this TRI achieved, or time for the rise of current. TRI, time the rise of current, it rise from after delay time here up to 90% of the values. Only then the VD start to deplete. Time falling of voltage, time fall voltage, time rise of current. Okay, so the total TRI and TFV will be the sum of T on, time of switching on, time delay plus time switching on, and time for the circuit to switch on. And then for switching off, we shall see here when the circuit is switched off, so we still have a delay also. You put out the gate signal, you have a delay, TD off, time delay for the switch to respond for off operation. So we have here the reverse, the rise of voltage up to 90%. Only then the current will drop or start to block. So we have here time falling of current, time rise of voltage, time falling of current will be the component of T for switching off. So TD off, TC off. So that's why when you calculate your switching losses, you shall refer to individual data sheet, which shows you how much actually the response time of our switch. So you can see here on characteristic, dynamic characteristic. This is for NTD 1210 just now. So this is switching characteristic. We have here time for on delay time, TD on, and rise time of delay time, and means that TD on we have to plus with T rise. So this is the on time element, and so this is TD off and T4. So this need to be included in our calculation to find what is the switching losses plus connection losses of the certain device that we are applying at our circuit. So we can use typical, we can use maximum, and so either one. So in your design letter, maybe we put maximum first. If not achieve your target, you can use typical. So if in between your target is achieved, so you can pass, or you can allow your system to be market or being produced mass pro. If not, so you have to reject or select new items or new parts or new design okay. So that's how the approach is okay. Then where's the okay, as per what we have circulate in terms of formula that you should follow or use inside your exercise. So the P on, power on, is depend on the how much energy during switch on times switching frequency. E on is calculated by how much the V times I times the half cycle of your switch on time, and T on is equal to T on plus T rise. So this one you can get from the data sheet. So total for switch on and switching on, total for switching off, the losses, and switch on and switch off losses. So energy off here, energy on here. This is your P on and P off, the switching losses. Then you add up with your conduction loss, so you will get your total PD and total PD. So P conduction plus P switching is your total PD. So please proceed with the example here. I will provide in terms of their answer. So how what are the expected output losses of the system. With this example, I shall provide